Hi, everybody. Welcome. Today we're going to continue with the Greek math. And I have a lot of stuff planned for today, but I'm going to try to go at a reasonable speed. So we're doing Greek geometry tomorrow also. And whatever I don't finish today will get put into tomorrow's, and maybe we won't do as much of the Greek geometry as I have prepared for. So let's take a look. The first theorem I want to show you is the last proposition of book 1 of Euclid's Elements is the proof of what we now call the Pythagorean Theorem. Now, we have seen in the Chinese math unit a proof of Pythagorean theorem. They called it Kogu theorem, that involves dissection, where they split up a squared and b squared into 5 pieces, and then they reassembled them to become c squared. Well, the Pythagorean theorem proof in Euclid's Elements, and it seems like the first book of Euclid's Elements, the whole purpose of it is to prove the Pythagorean theorem, because that is the last proposition of that book. Everything kind of leads up to it. It has a very intimidating diagram that looks like that. Can I make it bigger? Now that's a pretty famous diagram. You can see that it has a right triangle over here. Make it red, right triangle. There's the right triangle. Is the right triangle where the right angle, where the hypotenuse is like the base of the triangle? And then it has these 3 squares. That one, I'll call that smaller one a squared. And this square here is b squared. And this square on the bottom is c squared. Now, there are also a bunch of other lines. Well, not a bunch. Well, one, let's see, how many extra lines are there? There's also this line here. It's basically the altitude drawn to the hypotenuse, but then it's extended down. So that's one extra line. Then there's this line going from B to the corner of this square. And then there's this line, 3. Then there's this line and that line. So there's 5 extra lines drawn into this picture. Now, to understand the proof, I want to first show you that if I have a rectangle, and I take the base of this rectangle and make that the base of a triangle, and I put the third, so these are going to be 2 vertices of a triangle, but the third vertex is going to be either on the top line, top segment of the rectangle, or anywhere on the continuation of that line. I'm going to put it out there. Let's give some numbers here. What if the rectangle is 10 by 4? So here's a question for you. Is there enough information to get the area of the triangle? What do you think of that? Is this yellow highlighted triangle, is there enough information, or do I need to know more about angles or anything like that? What do you think? of that yellow triangle. We do know the base. We don't know any of the other sides of the triangle. Is that okay? Okay, how many people think maybe we need more information? Like this just isn't enough. We need an angle. We need one of the other sides. Anyone think that this is enough information? And this is correct. Nina says the height is 4. Because in a triangle, the height's not necessarily one of the sides unless it's a right triangle. The height of a triangle, especially an obtuse triangle, we usually draw like that. That's the height. But that height is 4. So what's the area of this triangle? It is area of 20. So the triangle is half the rectangle. And that would be true. Here's, I didn't draw it that well, but here's that rectangle again. That would be true if the third vertex was there or anywhere on this top line. Okay, that's going to be an important part of the proof. I'm going to switch for a second, and I have a link to this. When you go to the Google Classroom for today's lesson, you will see a link. There's a lot of videos and different things, but one of the things in there is it says Greek geometry for Mr. Rubenstein. This is something I use with my classes where I teach high school. And I have this like book, it's called, and it's got a collection of these interactive geometric diagrams. So a lot of the stuff we learned is on there. And here, this looks like the relevant one. So you see here, this triangle. What happens if I go full screen? I don't know if that is a good idea. Okay, so take a look. As I move that third vertex, you see how that triangle, the blue one, is always half. It actually works with parallelograms. It doesn't have to be a rectangle. So here it is for a rectangle, but notice how that triangle's area does not change, which is surprising. It wouldn't be that surprising if the triangle's area did change. But take a look. That triangle's area does not change, and it's always half the rectangle. Or if that rectangle is a parallelogram, yeah. So that area of the triangle will be half the area. Of course, the formula for area is 1/2 base times height for a triangle, and for a parallelogram, it's just base times height. So if the base is the same and the height is the same, then the area of the triangle will be half the area of the parallelogram. Now, the Pythagorean Theorem, if you want to memorize book and proposition, it's going to be book 1, proposition 47. And I'm going to see what, can you tell me when I go, I'm going to click full screen, but because of the way this sort of Zoom works, it's not clear if full screen like does what I want it to do. So my question for you is, let me get the chat going. What do you see now? Do you see a nice full screen thing, or can you see all this? Or do you see nothing? Okay. So what you see here, this is the general idea of the proof. Here I have the right triangle and the three squares. And I have, remember how I said there were 5 lines drawn in? One of them was from A perpendicular to BC and making this nice altitude. And what that does is that line, that vertical line, separates the big square, the so-called C squared, into 2 pieces. One that's blue, I've made blue, and one that's red. And the plan is, and it's not easy to do this plan, but the plan is to prove that the blue square must have the same area as the blue rectangle, and the red square has the area of the red rectangle. And if that's true, if both of those things are true, they seem to be based on this stuff up here, then A squared plus B squared will be the blue square plus the red square will equal this blue rectangle plus this red rectangle, but those 2 rectangles together become C squared. So that's like the plan. And as you can see, when I change the dimensions of the right triangle, these 2 numbers still end up equal. That's the square, blue rectangle. This is the red square and the red rectangle. So that's like the gist of the proof. He's going to prove, Euclid proves that this must have the same area as that, and this must have the same area as that. Well, that's not easy to do. That's where the extra 4 lines come in. So I'm going to draw in now the auxiliary lines. Okay, so basically I drew a line from F to whatever that is, G, or C, sorry, F to C. And I draw a line from A to T. And in doing so, I form these 2 skinny triangles. Now, what I want you to notice is that this skinny triangle, FBC, it has the same base as this little square, and it has the same height as it, kind of like we saw before, that configuration. See here, it's FBC. FBC is 2.82. Oh, sorry. FBC is 2.82. Notice how that's half of the square, ABFG. I'm going to rotate this a little, which one rotates it? If I turn it this way, I can see that this blue rectangle shares the base with this other yellow rectangle, with this other yellow triangle. So it has the same base, but just like before, this third vertex of that yellow triangle is on the on the line going through the top side. So that means that the other yellow triangle is half the area of the little blue rectangle. So the plan is, if I can somehow use geometry to prove that the 2 yellow triangles have the same area, and since each one respectively is half the area of either the square or the rectangle, then that would also prove that the blue square has the same area as this blue rectangle. Let me go back to the iPad to show you those 2 triangles in more detail. Okay, here are those two triangles, pulls out of the, so here's the picture, and you can see the triangles are FBC and ABD. Those are the two triangles there. Now, if those two triangles have the same area, and each one's half the rectangle, one's half the square, then the square and the rectangle will have the same area. Well, these two triangles won't just have the same area, but I'm going to show you that the two triangles are congruent to each other. And to do this, to help you out a little bit, I'm going to come here, and can we just first, for a moment, just say that the small triangle is, the small square is a 3, has side length 3, and the, and this thing has side length 4, and this length. Let's just pretend this is, there's a 3, 4, 5 right triangle. Back to here. So FB would be 3. Is there any other line segment in this picture that would have to be 3 also? That's correct. And why AB? This picture, just looking at the triangles, it's not clear. Why should that be 3 also? But you are right. It is 3. Why is that? What from the original picture? Yes, they are both sides of this square. So because this thing is given to be a square, AB and FB are the same length. Now BD is 5. What else should equal 5? That's right, BC. For the same reason, BD and BC are both sides of the big square. Now, just to like make this simpler, let's say that this angle here, let's just say that I tell you that that angle is 53 degrees. So let's just say I'm making that up. But let's say that this angle here, this acute angle, is 53 degrees. If you don't mind, I'm going to separate the two triangles because it's when they're overlapping like that, it's kind of hard to see. So we've established that these are equal because they're part of the same square, and that these are equal because they're part of the same square. What can you say about this obtuse angle here? Anyone know what the measure of that obtuse angle is? Look at it over here. That's a hint for you. FBC. It's close. ABC is 53 because I just kind of said it was. It is pretty close, but it's not 127. It's close to both of those. But what is it exactly? It is 143. Why 143? The 90. Because remember, this ABF was a right angle. How did I know that? Because it was given that this is a square. So this other angle is also going to be 143 for the same reason. See, that angle is also composed of this ABC angle plus another right angle. Now, even if I don't know that ABC is 53 degrees, it doesn't matter. Whatever it is, FBC is 90 plus it. Oops. FBC is 90 plus whatever that shared angle is, and ABD is also that. So these two triangles are congruent by what's called Sas postulate. I mentioned yesterday, Sas is a fancy way of saying it's unnecessary to measure all 6 pieces of the triangles to check if they are congruent. If you have 3 pieces, but they're the right 3 pieces, that will be enough. So those triangles are congruent to each other. And if they're congruent to each other, then they also have the same area, because congruent figures have to have the same area. But remember what I said before, if, and I'm going to erase this part now. Actually, I'm going to come back over here to the GeoGebra page. So those triangles have the same area. And it's a little hard to know which one of these rotates it. And this yellow triangle is half the area of this blue square. On the other hand, if I rotate it this way, I can see that this yellow triangle is half the blue rectangle. So if the triangles have the same area and each one, and this is double the first triangle, the blue square is double the first triangle, and the blue rectangles double the other triangle. But if the triangles have the same area, double them is the same also, and therefore the blue square and the blue rectangle will have the same area. Oh, about the 90 plus angle? You can see it on here. So this angle that goes all the way from here to there, well, this piece is 90. There's a nice bright angle here. And then whatever this thing is added to it. Now, I said it was 53, but even if we don't know what it is, this plus this should equal this plus that, because each one is 90 plus the angle in the middle. That's right. They're all half the area. This one, FBC, is half the square, half the area of the square, whereas ABD is half this rectangle here. And you can see over here it says DAB is 4.75, and those are the two triangles. But this triangle is half of this, and this triangle is half of the rectangle. And check this out. What about the reds? Well, if I get rid of the first rectangles, if I get rid of those two triangles and instead draw in these other two lines, I have the same situation. This triangle is half the square, whereas this triangle is half the rectangle. But those two triangles, these other two yellow triangles, those are also congruent by SAS, because each one has a side from the red square and a side from the large square. And the angle is 90 degrees plus the shared piece in the middle. So when you put it all together, it looks like that. Now I have a video for this. Not only am I recording this right now, but I made a very nice 10-minute video of this, explained really clearly, with animation a bunch of years ago, and you could watch that also if you need to see that again. But that is the famous Euclid Book 1, Proposition 47, otherwise known as the Pythagorean Theorem. And that's the way they prove it. Side angle side, and the theorem that a triangle with the same base as the parallelogram and the same height as the parallelogram has half the area, which is kind of a fancy way of saying that a parallelogram's base times height is its area, whereas a triangle's 1/2 base times height. But it's even more dramatic when you see it, when you see it like that. Okay, and that's the first thing that I wanted to teach you today.
Professor, can you show us where to find
the video?
Yes, please.
Yes. If I come back to the browser, and if I go over to the class page, so on today's assignment, here's the assignment, the Google Doc. But the other 1, 2, 3, 4, 5, 6, 7, 8, 9 things are either videos, which includes this one, Euclid's proof for the Pythagorean Theorem, sort of a 9-minute version of it, but it's really nicely done with a lot of animation. And not only that, but down here it says Greek geometry. That would allow you to go to this page where you could actually like manipulate, and that gives you a feel for this also.
Thank you.
You're welcome. Okay, well, that was the first thing I wanted to show you today. I have too many things to show you, but I'm going to show you basically 90 minutes worth of stuff. However far we get in 90 minutes is how much stuff that we're going to do today. Yeah, so that's already posted. It's all, Nina, you have a link. If you go to the classroom assignments, there's already the links there. If you click on it, it will bring you right to the YouTube page. Okay, the next concept I want to show you. I mentioned that Euclid's Elements begins, Book 1, Proposition 1, was to construct an equilateral triangle. And later on in Book 1, they show how you could use perpendicular bisectors. They also teach you how to draw perpendicular lines from a point not on a line, like perpendicular to the line. But basically, they eventually get to how to make a square. And you need to be able to construct a square in order to do Pythagorean theorem proof that has squares in it. So making triangles, equilateral triangles with compass and straight edge is easy, and a square is not too hard. And a 6-sided figure, which I'm not doing, but it's not too hard either. But something that is very hard, is constructing a regular pentagon. That's a very difficult thing to do. And they don't do it until like, I forget what book it is. Let's see, is it? Not even sure which book it is. I think it's, might be book 4, let me take a look. I don't even know. It's somewhere in book 5 or 6. Anyway, I'm going to show you the gist of it. Here is a challenging question for you. Well, I'll start with a less challenging question. What is the measure of one angle, interior angle, of a regular pentagon? So I see 2 different answers. One that's 108 and one that's 180 divided by 5. which is 180 divided by 5 is 72. Now, it does look like an obtuse angle, and it is 108 degrees. Usually what people do to see that, you can split a pentagon into 3 triangles. So the 3 triangles, each one of them is 180 degrees. Like these angles add up to 180, and these 3 add up to 180, and these 3 add up to 180. So the 9 angles add up to 180 times 3 is 540. And it's 540 that you divide by 5. So now here's a really, really important question. See this isosceles triangle here, the one that's in the middle? Basically, you have 2 obtuse triangles and one. They're all isosceles triangles. Can you figure out what the 3 angles are of the yellow triangle? Everyone take a minute to ponder that question. It's kind of like a good thought-provoking question. My question is, what are, these 2 angles going to be the same, whatever they are, and this one's going to be different. Okay, so take a minute to ponder that, please. I see Geraldine says 72, 72, 36. Why do you think that? Where's that coming from? Like, how'd you calculate out the 72? Or if you calculate out the 36 first, how did you come up with that?
Sorry, hello, I stepped away. The 36, I did the 108 divided by 3, and I got 36 for that top one.
Ah, but how do you know for sure that it cuts it into 3 equal pieces? You are right about that, but there's nothing that like guarantees that those 3 things. You are right, by the way, that these 3 things are all end up being equal. But what in the picture made you like 100% sure that those 3 had to be equal?
Well, if I turn it, wouldn't I be able to form the triangle the other way too?
Oh, if you like rotate it onto itself?
Yeah.
But then you wouldn't get 108 degree, right? This 108 degree angle wouldn't be on top of that. So I think you did get the right answer, and you had an intuition that it was going to be 30, that they were all equal, and you were right, actually. But I see another way to get that is to take the 108 and say that means these 2 angles together have to be 72, which makes this one on its own 36. But we know that this corner angle is 108 also. So then you do 108 minus 36. Okay, but it is 72, 72, 36. You were right, but there was an assumption that you made that turned out to be correct, but it was a little bit risky.
Can you show the calculation again, please? I still don't understand.
Yes, the calculation. Let me erase some of the stuff so we can see that better. So if I draw this line in, if this angle is 108, but this is an isosceles triangle because it's a regular pentagon, so all the 5 sides are equal. So that means that these 2 angles together have to add up to 72 because all 3 angles have to add up to 180. But because it's an isosceles triangle, they have to be equal to each other. So that's why these two are both 36. So you okay on that obtuse triangle?
Yeah, I get it now. Thank you.
Okay, now there's an obtuse angle here also, but that's 108 because all the angles are equal in the pentagon. So this needs to be 72 so that they add up to 108 again. So the key to the pentagon
But if you,
is,
but if you
Yeah.
split it like any of the angles like in threes, it would still be like 30. Like instead, like you see how you did from A to D and then B to D and made that triangle there. If I made it instead from E to C, it could be,
I see. You're talking about like that?
yeah.
Okay, that's real interesting. So yes, you could do it from there also. Are you saying that's a way you could see why those three things are equal?
Yeah.
But that triangle, that angle's all the way over here.
Uh-huh.
So that's not that. This angle here is that. Oh, are you talking about this guy maybe?
I don't know.
Like,
Now I'm a little confused. Sorry.
yeah, you are right that you could put that triangle anywhere, but where you're not going, like, so we have that angle, and if we go like this, we get that angle, and if we go like that, we get that angle, and if we go like that. So yes, there are a lot of angles there that are equal, but see
Okay.
this one and this one, they don't seem to really fit into there at all.
Okay, I see now.
Now, the thing the Greeks realized that was going to help them figure out how to create a regular pentagon with a compass and a straight edge. And doing it by hand, it's got to take like 20 minutes to create a regular pentagon by hand. We're going to be skipping over steps. I want to show you like what the insight is that makes it possible to create a pentagon. And the secret is that triangle. That 72, 72, 36. That triangle, the 36, oops. We call that a 36, 72, 72 triangle. You know, we talk about like a 45, 45, 90 right triangle or a 30, 60, 90 right triangle. Well, this thing looks like an N is just a bunch of random lines that can't figure out how to get rid of. The 36, 72, 72 triangle is an important piece. If you can create a 36, 72, 72 triangle, I know you might be thinking, well, with a protractor, I could do that. But the Greeks would not use a protractor, and not because they didn't have protractors. They had them. They would not allow themselves to use a protractor. They wanted to see what's the most I can do with the two simplest tools, the compass, and it's a straight edge, not even a ruler. A ruler has markings on it, a straight edge has no markings on it. So they didn't use other tools, not because they didn't have them, but because they were trying to see how far can I go with the two most simple tools, even though they had all kinds of tools. They had something called a flexible ruler. I don't even know how it works. I just read about that they had many tools that they made. If you could somehow produce a 36, 72, 72 triangle with a compass and a straight edge, here's what you would do with it. I think I have it on the next slide. So the general plan for making a pentagon is this. Step one, somehow make a 36, 72, 72 triangle. How that's going to happen, I'll tell you that in a few minutes. But let's just say we know how to do it. Step two, they want you to draw a circle. Every triangle can fit. There's a circle that fits around perfectly around any triangle. I'll just tell you that that's true. And you could find the center of that circle by taking the perpendicular bisector of any two sides. And wherever they come together, that would tell you the center of the circle. And then you could just draw the circle through any vertex, open the radius to any vertex, and the circle will definitely pass through the other two vertices. So that's step 2. And again, I haven't told you this thing about circumscribed circle, but I'm just telling you now that it's a fact that if you draw a perpendicular bisector of two sides, they will intersect at a single point. And if you make a circle with that point as the center and a radius, so the circle goes through any of the 3 vertices, it will always go through the other ones also. And of course, we know how to do perpendicular bisector. That was from yesterday. And then the third step is to bisect the two 72-degree angles. And if you do that, you'll have the perfect pentagon. So we got a couple of perpendicular bisectors, a circle, a couple of angle bisectors. But what we don't know how to do, and it doesn't even seem feasible, how am I going to make a 36, 72, 72 triangle without a protractor? Nina asks, did you want to see the plan again? Okay, so the plan was somehow to create the 36, 72, 72 triangle. How? We'll get to that. Step 2 is to make a circle around it. Now, making a circle around a triangle, that itself is its own problem. If you take the two perpendicular bisectors of any of the two sides of the triangle, where they come together is the center. And then if you make the circle so it passes through one of the points, it will definitely go through the other two also. So I'm not drawing the perpendicular bisectors of this right now. Let's just say I know how to make a circle around. And then I know how to do angle bisector from yesterday. And where the angle bisectors hit the circle are the other 2 points, vertices of the pentagon. That's just the plan. I haven't, Nina, told you at all how to do step 1. I'm going to move over to the GeoGebra for a second just to show you the plan, like in action. Oops. Oh. Hold on a second. Where is it? Golden ratio construction. No. Oh, here we are. Pentagon. 36, 72 triangle, circle around it, angle bisectors, pentagon. That's like the plan. Okay, back to the iPad. So the mystery now that the Greeks were able to solve is, how would I possibly create a 36, 72, 72 triangle? It just doesn't seem really that possible. Well, can we pretend for a second that the two legs of this triangle have length 1? And if I could somehow figure out what the length of this bottom side is, let's just say that I found out that it was 0.62. Let's just say I somehow figured that out. That would mean that if I made a line segment of length 0.62, and then I opened up my compass to length 1 and made like a circle with radius 1, and then did it again with this center, that is, and did it again from here, those circles would come together and it would create the 36, 72, 72 triangle. So if I can figure out, I'm not saying that it is 0.62, but I'm just saying that if I can somehow use math to figure out what the dimensions of how big is the base in relation to the sides? Is it 0.62? It definitely looks like it's smaller, but is it like 0.5? Is it half as big? Is it 0.4? Is it 0.6? You know, what is it? If we can somehow get that as an exact value, and we can create a line segment of that length, then I can make this I can make this full triangle. I wrote 0.62, but let's say I don't know it at all. And here it comes. This is one of the more clever. By the way, how could you do this using high school math, like stuff that you've already learned? Because we know the angles are 36, 72. So does anyone know like a way? It's kind of cheating because they wouldn't have had access to do this. But how could you answer this question using like high school geometry, high school math? Let's just say. Ratio? Which one? Like how would that work? Do you mean if you already knew what the dimensions were, like in a 30, 60, 90? Side to angle? Oh, like it's double? Like you can't quite do that. The angles are twice as big. 72 is twice as big as 36, but the sides are not twice as big. So you can't do like a ratio like 72 to 1 is equal to 36 to x. But this, you could answer this with high school math. Maybe it would help you if I drew a line down the middle. This is an isosceles triangle. So this would turn into a 72. This is a right angle, 18 degrees. And let's just call this y instead of x, just so that it's half of x. How would you do that question? And maybe I'll erase the other half. How would you do that question? Well, we don't know the area of that triangle. All we know is the two angles. A proportion like 18 over y and 90. Angles aren't always, it's true that the bigger size across from the bigger angle, but it's not like proportional. Like if like in this case, 72 is 4 times as big as 18, but that size, not 4 times. Yes, you would use trigonometry. You would say tangent. The tangent, actually, I probably wouldn't use tangent because it's the hypotenuse that's known. I'd use one of the others. I think I would say sine of 18 is equal to y opposite over hypotenuse. So y would be sine of 18, which does turn out to be 0.62. By the way, if you forgot your trigonometry, it's not really part of this course. I just thought it would be good opportunity if some people know their sine, cosine, tangent, they can see that they would be able to use modern math to answer this question. Oh, it wouldn't be 0.62, sorry. It would be 0.31 or something. But then we'd have to double it because there were two of them there. And then it would become 0.62. So you could use trigonometry for it. But that's not how Euclid did it. Euclid did not have trigonometry. Trigonometry was not invented until about 400 years later. And most triangles are impossible. Like if I said like 32 degrees and made these 74, 74, that wouldn't be possible without trigonometry. There is something special about the 36, 72, 72 triangle that it's possible to work out the length of that bottom side without a trig chart. And I'm going to show you how now. If I draw this extra line, I'm going to draw this extra line. This is going to be an angle bisector. If I bisect that corner angle, this is saying right now, is that an A? Yeah. So I have triangle ABD, the original triangle. And let's just throw this guy in, we'll call him C. That angle bisector has split our 36, 72, 72 triangle into two triangles. An obtuse triangle and an acute triangle. And here's a challenge for you. What are the angles of these two triangles? Take a minute. Yellow and purple. What are the angles for the yellow triangle and for the purple triangle? Well, they're obtuse and acute, that's true. But what are is there a way to get the exact angle measurements of the other two angles in each triangle?
Wouldn't the angles from where you drew that little point be the same?
Yes. So what are those? What are those?
I'm not sure yet. Sorry.
Right.
Hold on.
What was the angle before it got split in half?
A was 72, so if you divide it by 2, it gives you 36 on both sides because you did a bisector.
That's right. So the purple triangle is 36, 36, 108.
Yeah, because you subtract that from 180.
And the yellow triangle is 36. And what's this angle there that hasn't been identified yet?
180 minus 108.
That's right, which happens to be 72. So the answer to that question is that the purple triangle is 36, 36, 108. And the yellow triangle is 36, 72, 72. Anyone think there's something significant that happened there? Anything significant? If I took any, this is like an unusual thing happened here. Because what's special about the yellow triangle?
Well, it's a 36, 30, isn't it a 72, 72, 36? Like what we
That's right. It is similar to the original triangle, which only happens for this 36, 72, 72 triangle. If I took any other triangle that you could imagine, for instance, a 32, 74, 74, and I did that same trick, this guy here would not be similar to the original. But only for the 36, 72, 70. That's a special property that's only true of the 36, 72, 72 triangle. That when you bisect the angle, it splits it up into two triangles. And one of those triangles is similar to the original. I'm actually going to draw those triangles, the original one, the big one, and the yellow one side by side, because it's confusing when one's like inside of the other one. So here's the original one, 1, 1, x, 36, 72, 72. And here's the small one, the yellow one. I'll go like this. This is A, no, A is the vertex. This is AB also. So here is an important question for you. Can you tell me about these other two sides of this yellow? That's the yellow triangle. We know X, because that X is right here. That's side AB. But what about the other two sides? What can you say about them? Same as what? They're both X? Or it's 1 and 1? They're both X? It's not equilateral. AC does equal X. So let's put that into the picture. But now here's the big question. What about BC? Do I know anything about BC? BC doesn't equal AB. It's smaller than it. And it's not 1, because 1 is actually bigger than X. X is a little bit less than 1. And it is CB, so maybe we should go back to the picture that it came from. This picture. Maybe looking at it in this context. I need to erase a bunch of stuff because it's getting a little crazy here in this picture. Okay, so here's this. I have 1. I have X. This entire piece is 1. Okay, get ready for a very slick thing. We know this is X also, because that's this side. Here's what we don't know. And here it comes. What about the mysterious purple obtuse triangle that we haven't talked about at all? What's true? What do you know about the purple triangle? Like, what's one thing that you know about it? We haven't mentioned it really much, but that purple triangle is kind of important right now. What kind of triangle? It's obtuse, but what else? It's obtuse triangle because that angle, DCA, it's isosceles. Because remember, this was 36 and that was 36. That happened because the 72 got bisected, and it just so happened 72 is twice as big as 36. So what can you say about this piece right here that I'm making? It's not AB that equals X, but DC, this equals X, because this X here is part of both triangles, both isosceles triangles. It's part of this one, so that's X, but it's also part of this one, so that's X. So what does that make for BC? if this piece here is x, and yes, that is 1 minus x. And I believe if I go back to the that GeoGebra page, 36, 72, 72 properties. I have a nice thing here. Oh yeah, check this out. I think you'll like this. I could either not show the angle bisector or show it. But when I move this slider, look what happens. So you can see them next to each other. Although you lose the whole 1 minus x thing when you do that. It's easier to see when they're together, but. Okay, let me go back to the iPad. Okay, we're almost done with this. So here are the two triangles side by side. That's a lot of x's. But these are similar triangles. So what proportion can I create? It's going to have a lot of x's in it. But it's going to lead us to the answer. That's right. 1 over x, big side over short side in the first triangle, is equal to big side over small side in the other triangle. Now, when you cross multiply, you get 1 minus x equals x squared, which turns into 0 equals x squared plus x minus 1. Well, that's getting pretty ugly. How do we finish that one out? Won't be able to factor. I see formula. What formula specifically? Quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac over 2a is negative 1 plus square root of 5 over 2. Which does equal about 0.62. Yeah, completing the square would work also, except the x has a coefficient of 1, which is odd. So it's a little bit, you'd have to deal with fractions, but yes. Well, what we just figured out was the exact length of the third side of the 36, 72, 72 triangle. And if that is the length of the third side, that gives us a recipe for creating the triangle. Because here's what I would do. If I want to make something like, if you don't mind, I'm going to write it as square root of 5 over 2. Sorry, I'm going to write it as square root of 5 minus 1 over 2. I hope you don't mind. I write it that way. It's equivalent. Square root of 5 minus 1. Wait. Yeah, 1.23. Hold on a second. I'm doing it on a calculator just to make sure that I didn't. Yeah, 0.6180. Well, if I want to make a line segment that is that length, here's the sneaky way of doing that. Step 1. make a line segment of length 1 and a line segment of length 2 and make like an L-shaped thing. Step 2, connect these 2 points. How long is the hypotenuse of this right triangle? It is the square root of 5. Well, that's convenient. Step 3, make a circle like that. How long is that red line segment now? Yes, you're right about that. It is, the red line is square root of 5 minus 1 because this whole thing is the square root of 5 and this little green piece is 1. So it's, so how do I get from there to the what my goal was? Oh, sorry about that. Let me see if that's better. Let me see if I can. Here we go. Okay, but the goal was square root of 5 minus 1 over 2. Anyone have a thought of how we can get that? A line segment that has that length? Simpler than that, than dividing by the other leg. I have a line segment, a red line segment that's square root of 5 minus 1, but I want to have a line segment that's square root of 5 minus 1 over 2. It's one of the constructions we learned yesterday. Midpoint is correct. If I then found the midpoint, which I'll make blue, then this piece here would be square root of 5 minus 1 over 2. And once I have that, I can finish it. Let me show you a pretty cool screen. If you look at the screen now, I can actually go through the steps one at a time. So this is creating the square root of 5. Oh, rats, I'm doing it a bit of a different way, but at least it'll be fun to watch the construction appear. Sorry, I did a bit of a different way. I realize now, but that's the gist. So what I wanted you to learn from this whole thing is, one, that a 36, 72, 72 triangle is a very important thing. That we're able, that because we can use math to figure out the proportions in a 36, 72, 72 triangle, we could use those proportions to eventually create a 36, 72, 72 triangle. If you're wondering, like, that's just one side of the triangle. If you're wondering, like, what about the other two sides? If this blue thing is just one side, well, all you would do is make an arc of a circle with radius 1 from this point, and an arc of another circle from that point with radius 1. And then if you connected these things together, you would have 36, 72, 72 triangle, which you would then have to draw a circle around, and then you'd have to do 2 angle bisectors, and you would have your regular pentagon. But for our purposes, I think the most important thing for us is this, is knowing that it's possible to find the sides of a 36, 72, 72 triangle using algebra. This number is related to something called the golden ratio. Maybe you've heard of this before, that if you have a rectangle, let's call this A and this 1. And if the rectangle has the dimensions that the big side, hold on a second, let me go this way. If I have a line segment, and there's a point on the line segment, so that the ratio of the big side to the small side is equal to the ratio of the entire thing, to the big side, that ends up being about 1.62. And that 0.62 is similar to the 0.62 from the other thing. Okay, so that is the next thing. I think I want to give everyone a 5-minute break and then come back. So meet me in 5 minutes.
Thank you.
Hi, everybody. Welcome back. I think that we'll go for till about 4:30 today, so it's a little longer than I usually do. But from what we've done today, it took a long time. It's taken about an hour and a half already. But the main thing so far from today is that you have an understanding of the basic idea of the Pythagorean theorem proof, just like the gist of it and like what the plan was, and that you have an understanding now that a pentagon has a hidden 36, 72, 72 triangle, which itself, by almost some kind of luck, we have the ability to calculate out the proportions of a 36, 72, 72 triangle using similar triangles. And that those measurements would enable us, with some ingenuity, to actually draw a regular pentagon. As a challenge, you could make a regular pentagon. It would take about a half hour, I guess, to do all the different steps, but it's pretty satisfying when it's all done. Okay. Again, I'm not going to do all, and I'm going to alter the homework because I'm not going to finish all the stuff. I'm just going to move. I didn't expect to get through all of the topics today, so I'm going to move a bunch of them into tomorrow's lesson. And it just means there'll be a few Greek topics that we don't end up doing, but that's okay. I'd rather do fewer topics, but do them carefully so that people know them. Yes, this means that the homework, which currently is, let me take a look. The homework, you'll still be able to do 1 and 2. You'll only be able to do Yeah. Right now, you're only going to be able to do questions 1 and 2, like right now. But, and that would end up being the homework. But I think I will get us through question 3, 4, 5. I think I'll get us to question 6. So 7, 8, 9, and 10 are going to be for tomorrow. Okay, so we're only going to do 1 through 6. I'm going to make a note on the document right now. 6, and I'm just going to say, I'm going to put right in there, stop here. Well, you don't have a final. You have a final project. Oh, except for like a delta math thing. So you should know that next week is the last week, and I'm not going to be running a class, I don't think, on the last day. That's going to be like for you to take time to be working on, even the last 2 days, to be working on your projects. I think on Wednesday, I'll probably have I'll come and answer questions, and Thursday is when you'll turn in your project. Oh, I better post it there. I mean, the project is going to be about a 4 or 5 page thing where you're going to show how you would teach one of these topics to your students. Because history of math, some of these concepts, maybe like constructions or whatever it is you learned, I want to see how you would like teach it to your students. Like a little unit plan. I'll make some kind of rubric for you, what I'm looking for, like an outline of what the lessons are, a little reflection about what you're going to keep in mind, then like a lesson plan. Okay, let's see what you need to know to be able to do questions 3, 4, 5, and 6 today. There is something in math extremely famous known as the, oh, I think this iPad needs to be moved up. One of the most famous things ever in math are what's called the 3 problems of antiquity. Hold on. iPad froze. That's happening. Come back here. Okay, the 3 problems of antiquity. If you type that into Google, 3 problems of antiquity, you don't even have to say 3 famous math problems. You could just type in 3 problems of antiquity. I'm on a different page here, but let me just go into Google for a second just to see if I'm not lying about that. The 3 problems of antiquity. And yep, everything that's coming up. So you don't even have to say math. You could say the 3 famous math problems of antiquity, but these problems are so important and famous in the history of math that you don't even have to say they're math problems. There are only 3 things that are known as the 3 problems. It's like the 7 wonders of the world. I mean, the 3 problems of antiquity. These 3 problems kept mathematicians busy for 2,000 years. So they were first proposed in like 300 BC, and they were not resolved until the 17 or 1800s. Oh, hold on one second. Hi, everyone. I'm back. So what are these three problems of antiquity that have their special name and that have kept mathematicians busy for thousands of years? Well, the first one, you know how yesterday we saw that it is possible using a compass and a straight edge to bisect an angle bisector? You could also cut an angle into 4 pieces. You can cut a line segment into any number of pieces, but they were unable to figure out a way to trisect an angle. And trisecting an angle is the first of the 3 problems of antiquity. Ah, Cheryl Ann knows all 3. Where'd you learn those? Oh, you Googled it. Okay. The second problem of antiquity is, while it's possible to square a rectangle, to make a rectangle that is the square that is the same area as a rectangle, and it's actually possible to square any polygon. Take a polygon and using compass and a straight edge, create a square that has the same area. They were unable to figure out a way to so-called square the circle, which means making a square that has the exact area of a given circle. And the third problem is a little bit weird. It's called doubling the cube. Whereas it's possible with a compass and a straight edge, if I have a square whose dimensions are, let's say, 2 by 2.
Is this okay to use those?
And it has an area of 4. If I wanted to make a square that has double that area, it would be very easy. I would just take the diagonal of the square and make a new square that has that diagonal. And this area would end up being 8. So that's because the diagonal of 45, 45, 90 would be 2 radical 2. And the area of that square would be 8. So doubling a square is easy. Doubling a cube, though, given the dimensions of a cube, I want to make a cube that has double the volume. That requires making the side like a little bit bigger. And that also was, well, they didn't know it was impossible. They just thought it was really hard. But those 3 problems kept mathematicians busy for thousands of years until they were all proved to actually be impossible with a compass and a straight edge in like the 1700s and 1800s. So for thousands of years, these 3 problems. And if I were to give a final exam, if we were like in person, one of the questions on the final would be, name the 3 problems of antiquity. Because that's, no history of math course could be complete unless these 3 problems are mentioned. I want to spend a few minutes telling you today about some ways people cheated, I guess, to trisect an angle by cheating. How could I cheat? What does that mean, cheating? What would qualify as cheating?
You want to get the wrong and easy way. Oh, I thought you were muted.
Divide by 3, how so? Like, how do I do it? What tool would I be using that would be illegal? Yes, if you use a protractor or something. Well, compass is allowed, but a protractor would be an illegal way of doing it. So that's one way of cheating, but protractor would be like really, really cheating. They came up with other ways of cheating. Which aren't as bad as using a protractor. Like, using a protractor is like such bad cheating, but maybe if I were allowed to use some other kind of curve, like an ellipse, or just something else that you can't make with a compass, it would be like less cheating because it would still be based on geometry. Well, I'm going to show you a couple of solutions that cheat, but they don't cheat so bad that they use a protractor. But they cheat by either using another curve or by doing something with the compass and straight edge that's like not possible to do accurately. And the first one is going to be the great Archimedes method. So here's what Archimedes says. I have a 75-degree angle. I'm just saying 75. Let's say we don't even know how big it is, but I'm just making one that's 75. Oh, hold on 1 second.
Every 30 seconds, I thought you just do it. Okay.
So I'm back. So here's what Archimedes says. To trisect the 75-degree angle, this is the center of the circle, I extend the diameter to the left like that. And I am going to go over to the GeoGebra page. Hold on a second. Archimedes, where is it? Hold on. Oh, that's the wrong. Trisecting an angle. There it is. And you have access to this page. Okay, here's what Archimedes says. He says that I make a line from what I call D there. See that? This line I'm making? I pick a point outside the circle. See how A is the endpoint of the diameter? And this point F, there's a lot of places that I could put it. And depending on where I put this F, you connect F to D, and it will hit the circle at G. So if I put F here, FG is real small, and GD is some length. But if I put F out here, GD gets smaller, but FG gets bigger. What Archimedes says is, if you could make this so that FG is exactly the same length as the radius. Now the radius in this case is 2.61. So this is about as close as I can get. Archimedes says that if you do that, then this angle, DFC, will be exactly 1/3 of DCB. And he's right about that. We'll see why that is. But for now, you can actually see they're divided here, and you see H equals 3. If I put F anywhere else, see how this H, which is the ratio, it's not 3. But if I move it out so that FG is the exact same length as DC, if I can accomplish that. Now, accomplishing that is its own problem, because how do you do that? But he says that if I could find this perfect point F, so what you should know is the perfect point is the point that would make, if you connect F to D, that FG would be the exact same length as the radius of the circle. If you can do that, then DFB will always be 1/3 of DCB. Let me come back to the iPad to show you why that worked. Okay, so what Archimedes says is there's some point. Where is it? Somewhere over there. if I could somehow manage to make it so that this equals that, which, like I said, it's really hard to find that point, and actually it's impossible to find that point using a compass and a straight edge, even though it seems pretty reasonable. But what we've done, I forget what letter, did I call this D? No, G. This is the configuration. So there's only one spot where F could be. Anywhere else that I put F on this line, and then I connect F to D, this FG will not be equal to this OD. But there's like a perfect spot. And if we can find it, which we can't, like there is a spot, but we can't like use construction to find it. Archimedes says that if you find that point, you will have achieved angle trisection. And let's just see why that is. Like why, if I actually have this picture like this, it will, like I'm telling you that angle OFD is 25 degrees now, but it's not obvious why. And let me show you why it would be. Not just because Archimedes says it. Here is an extra line. And I'm going to call this angle X right now. Can I also just like, you might find it easier if I stick some numbers in. Like what if I tell you the radius is 5, just to tell you that. And that means that FG is 5 also. How big is GO? You can type that in. Also 5. It's the radius, so GO and DO are equal. So what can you say about angle? What can you say about angle GOF? Yes, it's X also, because that is an isosceles triangle. If these two sides are equal, it's an isosceles triangle. Now, you remember yesterday I told you about the exterior angle theorem? What does the exterior angle tell us about angle DGO? What can you say about angle DGO? Yes, it is 2x. It's x plus x. So I'm going to write in 2x there. If you don't believe that, let's imagine this is 20 degrees and 20 degrees. And then I went like this. You can see that this would be 140, which would make that 40. So it would be equal to double those if you wanted to use like actual. Now look at this God triangle, GOD. Any observation about the God triangle? Maybe I should say this. How long? Yeah, they're all. There's another 5 there. GO is 5. It's another isosceles triangle. So what could you say about this angle here, angle GDO? You could. So GDO, we can go simpler than that. It's not quite X. Like that. So what can you say about GDO? It is 2x. Isosceles triangle has equal base angles. Oops. Now I'm going to do something very sneaky. I am going to erase everything except for the 2x. I even erased line segment GO. What's the relationship between the 75 now? Because he hasn't been used at all yet. And these, what can you say now about, can you make an equation now? It's an exterior angle. 75 is exterior to this big FOD triangle. So what can you say now? Yes, it's the exterior angle. So x plus 2x equals 75, or 3x equals 75, or x is 25, which means it's exactly 1/3 of the 75. So that's very slick. And that's Archimedes' method of trisecting the angle. But it's cheating because this point F, even though it definitely exists, and there is a special point F that would make FG equal to DO, even though there is a special point, there's no way to actually locate that point using the tools of compass and straight edge. So it's not considered a solution to the impossible problems of antiquity, but it's still very clever, and it's like a new problem that you could work on, but it's impossible to find point F. Still, very clever Archimedes proof. Okay, I'm going to show you one more thing today. And I know we're running out of days, and there's certain things that I definitely want to tell you about, like the problems of antiquity. So today's like a marathon day, but the truth is the homework is very short. Like each homework question takes like 2 minutes or something. So the homework's only like 15 minutes long, I think 20 minutes. So it's a much shorter homework, even though the lesson is much longer. There's the Archimedes construction. Okay, Archimedes also came up with another way to trisect angle. With something called the Archimedes Spiral. And, a spiral is like a thing like that, but an Archimedes spiral is a very specific type of spiral. So let me come back to the, I'm going to post the video. It has to process, and I'll have it. Someone's trying to get in. Thank you. Okay, they're coming in. This homework's much shorter, Cheryl Ann, you'll see. Because the way these questions are, it's like numerical answers. You'll see when in fact, if you look at the homework, literally look at question number 1 here. Let's do it together. Question 1, if square GABF has area of 9, what's the area of rectangle JLDB? All together now. That's right. Look at question 3. If angle BFD is 25 degrees and AB equals 10 and FG equals 5, what's the measure of angle BCD?
So you just want us to write the answers. We're not showing any work.
Oh, no, there's no work to show on those.
Okay, gotcha.
Number 3, it's not, BCD? BCD is this one. It's triple. So you see, that's what I'm talking about. Question 2 is a little bit longer, but did I? Oh, I don't have any questions about the spiral. I might throw in a very short question about Archimedes spiral. But let me come back to, sorry, okay, so let me go back to the GeoGebra page. Where's my Archimedes spiral? There's one, but that's not the one I want. Trisecting an angle with a spiral. Okay, here's a Archimedes spiral. Okay, and here's the property of the spiral. Watch carefully. Now, let me make this a nice. So as this point B, like a clock, goes around, you see point B going around the circle counterclockwise. So first focus on the point going around the circle. Now I'll go back. Now look at the at the center point. It's moving on that radius at a very steady rate. So that when I'm halfway around the circle, that point has made it halfway towards the circumference. And when I'm a fourth of the way of the circle, the point has made it a fourth of the way of the circumference, and 3/4 around, I'm 3/4 to the circumference, and finally, those points, see that? They get there at exactly the same time. That's called the Spiral of Archimedes. And I'm actually, in the homework, this is going to be my last topic of today, which means that there's only going to be, I'm going to say stop here, but this is actually going to, I'm going to add in two other questions about what I'm teaching you right now. They're pretty short, but I'll just say spiral question 1. Those are to be filled in later. So now that you know what the Archimedes spiral is, here is an example of one of the homework questions. Or a question I could ask. Whoops. So an example of a homework question would be, if this line segment is length 12, and this angle, this will be one of the homework questions that it only takes a few seconds. Whoops, there's a lot of, and this angle is 120 degrees. There's a lot of, and this angle is 120 degrees. My question is, how long is that line segment? I'll make it another color. It's going to be a question just like this, but it won't be 120 degrees. It will be like some other angle. I'm hoping to put in the questions in the next like half hour. So what's the answer to this question? How big is that red line segment? Stephen E says 4. Yes, why 4? You're right. That's right. So let's say it's theta over 360 times the radius. In this case, 120 over 360 times 12 is 1/3 times 12 equals 4. And I'll make another question like that, and the only difference is that I'll change these two numbers. But I like to make the picture accurate looking, so I put that up after class. Okay, so that's what question 4 on the homework is going to be, something like that. Okay, final thing for today in the last 5 minutes. The spiral of Archimedes is another way. The other questions are going to be tomorrow night's, over the weekend's homework. Okay, here's back to Archimedes. So here is the spiral. And now here comes how, if I have this spiral, incidentally, I can make individual points on this spiral, but you can't draw this perfect spiral with a compass and a straight edge. You can make individual points, like I can make a 120-degree angle. If AB is 12, I can make a 120-degree angle, and then I can make a line segment of length 4, and I could actually create this point, and I could do that for as many points as I want, but I can't do it for an infinite number of points, so I cannot make a perfectly smooth spiral of Archimedes. But I'm going to show you how I could trisect this angle. So this angle is now 118.8. Let me make it 144 degrees, because that's something I can trisect. Step 1. See this segment AB? We trisect that segment. Remember yesterday I showed you that it's possible to trisect a segment using a compass and a straight edge? Now you don't need both points of trisection, just the one that's closest to A. So this AB with all the primes on it is 1/3 the length of this segment A to this B. Step 2 is make a circle with center A that goes through that little B. And the final step is to join A and G. And you can see up here, angle BA and that thing, BAG, is 48, which is exactly 1/3 of 144. I'm going to go through those steps again. It's only 3 steps. Step 1, trisect the segment that goes from A to here. Step 2, make a circle. Step 3, connect A to G. And this new angle will be 1/3 of the original. Let me show you why that works, and that will be our last thing. That just the proof of that will be our end for today. Question 5 is going to be like the oh wait, where's the iPad? New share iPad. Where are you? Oh, question 5 is going to be about the trisection. I think it's just going to show, it's going to give like a thing and say, show how you would trisect it. Okay, so here's why this works. Let's use numbers now. Let's pretend this thing is 12. And if you don't mind, I'm going to call this 100. I'm going to call it 120 degrees, even though it's not. So what was established before, if this was 120 degrees? How long would that line be again? That green line? 4. Oh, can you do me a favor? Can we please change this to be 18 instead of 12? It'll be easier to illustrate. I'm going to make this radius 18 instead of 12 for our purposes. So now what would the green line be? It's no longer 4, but now it would be 6. Because 120 degrees is 1/3 of 18. It's 1/3 of 360. Now, yesterday, one of the constructions was to trisect. Just to remind you, like if I had a line segment of length 6 creating this trisection point is actually hard. Like you have to make like another line and you divide that into 3 equal pieces, and then you connect these, and then you make parallel lines. But let's just skip all those steps and just say somehow we're able to magically create the trisection point. So how long then would be this blue line segment that I'm drawing in there? Okay, that's right. That thing would be 2. Now the next step, which is a little bit cryptic, is where you make this weird circle. And then you connect. This is our critical point, where that circle hits the spiral. Now here's my question for you. How big is that pink line segment I just drew? That's right, it's also 2 because of that circle that had 2. Now, this angle, which was the goal, I'm running out of colors, this angle here, that, in this case, it's going to be 1/9 of 360, because 2/18 it means it's gone 1/9 of the way around. But if it's gone 1/9 of the way around, the angle is going to be 1/9 of 360, which is 40. So yes, we can see that it is 1/3. And in general, and here it is, the line segment is always proportional to the angle. Like when the line segment gets twice as big, the angle gets twice as big because it kind of grows at a steady rate in that way. So when the line segment gets 1/3 as big, when the angle's 1/3 as big, the line segment's 1/3 as big. And conversely, if the line segment's 1/3 as big, the angle would be 1/3 as big. And that is the kind of answer of why the spiral of Archimedes could be used to trisect an angle. Now, this is cheating also. Archimedes came up with 2 ways to cheat. Spiral of Archimedes would trisect an angle, except we can't create a spiral of Archimedes with a compass and a straight edge only. And the other one with the circle and the special point F also. Okay, so that's going to do it for today. Basically, what we did is we learned the Pythagorean Theorem proof from Euclid's Elements. We learned about how to make a regular pentagon with a 36, 72, 72 triangle. We learned that there are these 3 problems of antiquity: trisecting the angle, squaring the circle, doubling the cube. And we learned that there were 2 ways created by Archimedes of cheating a little to accomplish the first of the impossible problems. Tomorrow's lesson, we will do the other 2 impossible problems and show how they could cheat to get those also. Oh, the 40? Well, 2/18 is equal to 1/9. So the line segment, when the line segment grows to size 2, it's when I'm 1/9 of the way around the circle. And 1/9 around the circle is 360 divided by 9, which is 40. Here, I'm going to pause the video or stop the recording.